Looking at defining a system of equations and then also solving a system of equations, or at least the different methods we have available to us. So let's go and start by defining what a system of equations is. When we talk about a system of equations, we're going to keep it really simple in this video. Systems of equations, we say it's more than one equation. So more than one equation and more than one variable. Okay, so more than one variable. And we say basically solutions. Let's put this in a different color. We say solutions have to satisfy all of the equations. Solutions must satisfy all equations in the system. So basically this is systems in a nutshell right here. These things have to be true essentially. So here's what we're going to do. We're going to look at how one would necessarily solve a system, and just know this, when we look at this in this video, we're going to look at a system of two equations and two variables, and these are both linear constraints here. So we're going to be graphing lines for first few examples here, but we say, how would I solve the system? Well, the first thing we want to acknowledge is, if we were to graph both of these, what we would actually see is a graph of their solutions to their equations, because any point on the graph of an equation is a solution to that equation. So we're going to look for common solutions. So you notice that when you graph lines, especially lines, we say we have two forms we often deal with. So we say ax plus by equals c. This is standard form. We want to know this. Oops. Standard form. Okay. And then we say y equals mx plus b. And this is slope intercept. Okay. Where m is the slope and b is the y-intercept. Okay, so that being said, I notice that both of these are in standard. So when you graph something in a standard form, the thing that's important to put on here is this. We do this by finding the intercepts, okay, where it hits the x-axis and the y-axis. So we say the intercept method is what I would call this. We would plug in, an input of 0 here. When I plug in 0 for x, you would see that that term would just not matter anymore. You get negative y equals 0. So y must be 0. So we say 0, 0, and actually if I plug in 0 for y, I'm going to get 0 for x here. So it doesn't really help us. When you have something in standard form equal to 0, you're actually going to have to alter this to be in slope-intercept form. So if I were to put the y on the other side, I'd have x equals y, or in other words, I'd have y equals x, or 1x plus nothing. So this is just a line that has a slope of 1, so I say up 1 over 1, up 1 over 1, up 1 over 1. Basically, I get this entire solution set right here, and when you graph this, what you want to do is you want to make sure you label it with the original equation. So we say this is the set of solutions. This is all the solutions to this equation. So this is kind of a fascinating thing to be able to see them all. Let's go ahead and graph this other graph here. If I were to do an x and a y-intercept for it, so we say plug in 0 for x, plug in 0 for y. When I plug in 0 for x, I notice I get negative 3y equals 6, so y must be negative 2, negative 2. And when I plug in 0 for y, I get 5x equals 6, and others I get 6/5. So this is going to be an interesting graph here. We say 0, negative 2 is right here. If I were to go to 6/5 comma 0, that'd be 1 and a fifth. That's right in here somewhere, and then go up and over. I'm going to try to do this just by eyeballing it here. You have to forgive me for not getting this very well. We say 5x minus 3y equals 6. Make sure you label it. Essentially, we're looking for the common solution. So I did not draw this very well by hand, but I suspect that 3, 3 is on both of their graphs. And so what we're going to do is we have to verify this. We say, how many solutions does this system have? First of all, it has one solution. Recall that the solution to a system is, it has to satisfy all the equations in the system, and so that would be any point that they have in common. So we say solutions, how do we know that this is a solution? It has one point of intersection. So the first thing we want to establish here is this. When you look at the graph of a system, then we're looking for the points of intersection because that's the number of solutions it has. And then the other thing is this. We say we have to check this solution to see that it works. So if I were to plug in 3, so for instance I get x is 3 in the first equation, y is 3 in the first equation, 3 minus 3 is 0, and then if I were to plug these into the second equation, I get 5 3's minus 3 3's equals 6. We could check this. We say 15 minus 9 equals 6 and 6 equals 6. So this checks out on both equations here. So when we talk about solutions, we're really talking about finding points of intersection on their graph. So we could solve this system a few different ways. But essentially the first one, we say methods. Methods. Number 1 is graph. Graph. Look for points of intersection. Numbers 2 and 3 we're about to cover, but we say substitution. Substitution method, which is not a bad method. And then we say elimination or linear combination. Elimination. So we're going to cover both of these very, very quickly here. But it says, how might we have solved for these algebraically? Is there more than one way? Well, the first way is this. When you have a system, we're going to go ahead and block this off here. We're going to do substitution in this little area. We say x minus y equals 0. and 5x minus 3y equals 6. Substitution, we say, has 3 steps to it, but the first one is this. You isolate one of the variables in your system, and I think it'd be really easy to get x by itself. As a matter of fact, we got this equation x minus y earlier. We're going to call this like the altered equation when you do substitution method. What we're going to do is we're going to substitute, and down here we say instead of x, what we're going to write is y, because everywhere I see an x, we say x and y are the same thing. So we get 5 times this minus 3 times y equals 6. You notice I put in blank parentheses, and I'll throw in a y here, right here. And I get 5y minus 3y equals 6. So in other words, 2y equals 6, and I get y equals 3. So this just goes to support what we found earlier. I do want to point that y equals 3. This is our solution right here. And then to find the x value, what we do is we plug this back into any of the equations in the system, which I'm going to plug it back into this third equation here, where it says x is equal to y, so I'll put in a 3. And you can see that we get the same solution as we do up here. So this is our substitution method right here. We started by getting a variable by itself and plugging it into the other equation. And the last method is elimination, okay? And elimination has a goal. But essentially, looking at the original equation again, we say x minus y equals 0, 5x minus 3y equals 6. We want to find two variables that we can make their coefficients opposites of one another. So for instance, if I were to take this whole top equation, which I'm allowed to do this, times a negative 3, I noticed that it would make this negative y turn into a positive 3y. So I'm going to just transplant this equation down here. We would get negative 3x plus 3y equals negative 3 times 0 is 0. So this would be like my new system right here. And I could say, adding these together, I notice that I get positive 2x's. My y's cancel out and I get negative 6 on the right. So solving this here, this is a positive 6, sorry. I get x equals 3, and then, just like we did earlier, we say, well, if I know that x equals 3, let's go plug it back into its original equation. One of them, either one. I just noticed it was really easy to do it in this equation right here. So we say 3, so that means negative y equals negative 3, which means y equals 3. And again, I'm going to write this as 3 comma 3. So elimination means we're just going to make some of our coefficients opposites and then add these together and get our solution here. So we say, how did the solution relate to the graphs? Well, we say the point 33 is the point of intersection. And so, in other words, it is a solution. It is a solution to every equation in the system. And how do we know this answer is right? We can check by plugging back in, by plugging into original equations, okay? So this is how we refer to a system and how we solve them.